you know, when you pop the hood of a modern car, what you see is it's an absolute marvel of mechanical engineering.
Oh, absolutely. It's incredibly complex.
Right. Like you are looking at a system where hundreds of precisely machined parts are all working together. You've got the fuel injectors spraying these microscopic mists of gasoline.
Yeah, the timing belts keeping the valves from smashing into the pistons.
Exactly. And, the alternator converting rotational kinetic energy into electricity. It's all this perfectly synchronized ballet just to propel you down the highway at 60 miles an hour.
But the funny thing is, most of us never actually look under the hood.
No, never. We just look at the dashboard, we look at the speedometer, we check the
Yeah.
fuel gauge, we listen to the radio.
Right.
And when it comes to Bitcoin, it feels like the entire global financial system is doing exactly that. We are obsessed with the dashboard.
We really are. It's all about the price.
Yeah, we watch the price ticker flash red and green. We read the wild headlines about new all-time highs, and we argue about market capitalization. But today, our mission for this deep dive into the source material is to put on our mechanics overalls.
I love that. We're opening the hood.
We really are. We've gathered an incredible stack of sources for this, ranging from Satoshi Nakamoto's original 2008 white paper to some really dense technical documentation on the Lightning Network.
The Bulty specifications, yeah. Heavy reading.
Super heavy. All the way up to a mountain of historical network data, from the Genesis block to the 2024 institutional ETF approvals.
So we've got the full spectrum.
We do.
Yeah.
And we are going to look at the actual byte-by-byte mechanical engineering and the very precise economics that make the first and largest cryptocurrency tick. We aren't just talking about what it's worth.
Right, we want to know how it works.
Exactly, how it works under extreme pressure and why those very specific design choices led to it being known globally as digital gold. So, where do we start?
Well, I mean, it's the only way to truly understand the phenomenon, right? If you want to know what we are dealing with, you have to look past the financial noise and examine the underlying machinery.
Totally.
And to set the stage for you, we need to acknowledge that this machine wasn't built in a vacuum. We are building on a foundation of some very specific cryptographic concepts that existed long before 2009.
Okay, like what?
Well, we're talking about cryptographic hashes, which they act like digital fingerprints for data. We're talking about digital signatures based on elliptic curve mathematics.
Right.
We are looking at the concept of an append-only peer-to-peer network and proof-of-work consensus. Like for decades, academic cryptographers, cypherpunks, and computer scientists had been playing with these individual puzzle pieces.
So the pieces were already there.
Exactly. But it was in January 2009 that these concepts were finally assembled,
Yeah.
balanced against human economic incentives, and booted up into a working, self-sustaining system for the very first time.
Okay, let's unpack this, because the first thing our material makes abundantly clear is that to understand this system, we have to completely unlearn everything we know about how money works in a traditional setting.
Oh, yeah. You have to forget your banking apps entirely.
Right, because the documentation states, point blank, that Bitcoin does not have accounts.
None. Zero accounts.
Which, for anyone who has ever managed a ledger or even just looked at a checking account balance, sounds completely counterintuitive. How do you have a financial network without accounts?
It is arguably the single largest mental hurdle for anyone coming from a traditional financial or like a database engineering background.
I bet.
Because when you log into your bank's portal, or even when you look at how other major blockchain networks like Ethereum operate, they use what is known as the account model.
Okay, so how does the account model work, just as a baseline?
The easiest way to visualize the account model is to think of a massive centralized spreadsheet. There is a column with your name or your specific account number, and right next to it is a mutable field, a cell that holds your current balance.
Right, so if I have $100, that cell just says 100.
Exactly. It simply contains the integer 100. If you want to send someone $10, the bank's database servers do two things. First, they decrement your cell down to 90,
Makes sense.
and then they increment the recipient cell by 10. The balance is a stored objective fact sitting in a specific database row.
So it's just a number that gets constantly overwritten as money moves around. But this network rejects that entire premise.
Completely. In the entire Bitcoin protocol, there is no database row anywhere that says address X currently owns 3.5 Bitcoin.
Wait, really? It doesn't say that anywhere.
Nowhere. That aggregate number simply does not exist as a stored piece of data anywhere on the blockchain.
Okay, so what does it use instead?
Instead, the network uses a fundamentally different architecture called the UTXO model.
UTXO. Okay.
Yeah, that acronym stands for Unspent Transaction Output. Instead of maintaining a spreadsheet of account balances, the network maintains a giant global collection of discrete, individual chunks of cryptographic coin.
Like little digital gold nuggets.
Sort of, yeah. Each of these chunks was created as the output of some previous transaction, and crucially, it hasn't been spent yet. That is a UTXO.
So it's much closer to the cash in a physical wallet.
That's a great way to put it.
Like, let's say you open your leather wallet right now and you look inside. You have a crisp $20 bill and a $5 bill. Your balance is $25.
Right.
But the actual number 25 isn't printed or written anywhere inside your wallet. You don't have a magical piece of paper that updates to say 25.
No, you just possess two distinct, discrete physical objects, a 20 and a 5.
Exactly. And your brain, or your wallet software, does the math on the fly to say, I have $25 of purchasing power.
That derived quantity is the perfect way to understand what your Bitcoin software is doing. When you open your mobile wallet app and the screen tells you that you have 3.5 Bitcoin, it has essentially scanned the entire blockchain.
Or it asks a trusted server to do it.
Right, yes, a server.
Yeah.
And it has located every single unspent chunk of coin, every single UTXO that happens to be cryptographically locked to your specific private keys.
Wow.
It dynamically adds up the values of those discrete chunks in the background and presents you with a total. The balance you see is, technically speaking, an illusion.
An illusion.
That is wild.
It is a computed summary for your convenience, not a fundamental reality of the network's data structure.
But wait, sticking with the physical wallet analogy, if I want to buy a book that costs $22, I can't just take scissors and rip a tiny corner off the $20 bill.
No, the cashier would not accept that. Right. I have to hand the cashier both the 20 and the 5. I give them $25 of discrete bills, they put them in the register, and they hand me back $3 and change. A brand new, discrete chunk of money is created and given back to me.
Yes.
Does a purely digital network really operate that strictly?
It operates exactly that strictly, down to the literal byte. You cannot spend part of a UTXO.
Not at all.
Not at all. They are entirely indivisible when they are used as an input to a transaction. If you possess a single UTXO worth 5 Bitcoin and you want to send a vendor 1 Bitcoin for a service, you must consume the entire 5 Bitcoin UTXO in your transaction.
So it just melts the whole thing down.
Exactly. The transaction mathematically destroys that 5 Bitcoin chunk entirely, erasing it permanently from the global unspent set. In its place, the transaction creates 2 brand new UTXOs.
Okay, the payment and the change.
Right. A 1 Bitcoin output sent to the vendor's address, and a 4 Bitcoin output routed securely back to your own wallet. That second output is your change.
I'm trying to wrap my head around the engineering of this. If I'm building a global financial software system, updating a single balance field in a database seems infinitely simpler.
It does seem that way on the surface.
Right, because destroying and recreating millions of discrete cryptographic chunks of coin every time someone buys a cup of coffee sounds incredibly inefficient. It sounds like a massive amount of data churn. Why not just use the account model and subtract the numbers? What is the hidden advantage here?
You are touching on a classic computer science debate here. Updating a single cell is easier for a centralized server, absolutely.
Okay.
But in a decentralized network where thousands of independent computers around the globe have to agree on the state of the ledger without trusting each other, the UTXO model provides unparalleled security and efficiency.
How so?
Let's look at the first major advantage: parallelism and verification. Because every UTXO is a completely independent, discrete data object, validating a new transaction is incredibly straightforward.
Because it's not looking at a global balance.
Exactly. The network nodes don't have to calculate complex global states. They just have to ask one binary question. Is this specific chunk of coin currently listed in the global unspent set?
So it's just a giant set membership check. You either hold the $20 bill in your hand or you don't.
And because of this discrete nature, network nodes can process many transactions in parallel. If transaction A involves completely different UTXOs than transaction B, a computer can validate them simultaneously without them interfering with each other.
That makes a lot of sense.
Furthermore, the entire global UTXO set, the master list of every unspent chunk of coin on Earth, is surprisingly compact.
Really? I would assume it's massive.
Based on the network data we are analyzing, the active UTXO set hovers around 180 to 190 million individual entries.
Wow.
That entire database is only a few gigabytes in size. You can fit the entire state of global Bitcoin ownership into the active RAM of an off-the-shelf laptop.
The entire global ledger of who owns what, stripped down to just the unspent chunks, fits in a laptop's RAM. Okay, I have to admit that is highly optimized.
It gets better when you consider the second major advantage, which solves a notorious database issue called lock contention and race conditions.
Oh, race conditions. Those are a nightmare.
Right. In an account model, imagine you and your spouse have a joint checking account with exactly $100 in it. You both walk up to different ATMs at the exact same millisecond and attempt to withdraw $50.
Okay.
The central bank's database has to perfectly sequentially lock that account row. It has to process your withdrawal, drop the balance to 50, unlock it, then process your spouse's withdrawal and drop it to 0.
Right. It has to be perfectly ordered.
But if the database fails to lock that row properly, it might read 100 for both of you simultaneously, allow both withdrawals, and suddenly you've double decremented the balance. The bank loses money.
A race condition. Two systems racing to alter the same piece of data.
Yes. But with UTXOs, race conditions are mathematically impossible.
Because the coin is destroyed?
Exactly. A specific chunk of coin can only be spent exactly once. The millisecond it is presented as an input in a valid transaction, it is utterly destroyed and purged from the unspent set. There is no mutable balance field to accidentally double decrement.
So if two people try to spend it at the same time?
If two people try to spend the exact same UTXO at the same time, the network simply accepts whichever transaction reaches it first and destroys the coin. The second transaction immediately becomes invalid because the coin it is trying to point to no longer exists.
Yeah.
Once it's gone, it's permanently gone.
That makes total sense for a distributed network. You don't have a central server acting as a traffic cop to carefully sequence every action, so you need a data structure that inherently prevents double spending.
Precisely.
And the documentation also points out a major privacy advantage to this discrete structure.
Privacy is a huge factor here. Because there is no single persistent account tying all your funds together, your wallet software can and absolutely should generate a brand new cryptographic address for every single transaction you receive.
And for every piece of change you get back.
Exactly. If you receive your salary to address A and you buy a car, your change goes to a completely new address B. This prevents all your financial activity from being aggregated under one easily trackable public account number.
But people do still try to track it.
Oh, chain analysis firms can still use heuristics to try and cluster your UTXOs based on how you group them together later. But the fundamental architecture permits a baseline level of separation that an account model completely lacks.
But let's look at the other side of the coin. If the UTXO model is so great, why doesn't Ethereum use it? What are the developers deliberately sacrificing by sticking to this architecture?
The primary trade-off is statefulness.
Meaning
Meaning, if you want to build a complex smart contract like a decentralized cryptocurrency exchange or an automated lending protocol that needs to track interest rates, having a persistent mutable state is incredibly useful.
yeah.
You want your smart contract to know its current global balance, its current debt ratios, and its historical state at all times. The account model excels at that.
And UTXOs don't.
UTXOs are terrible for that. They are clumsy and incredibly difficult to program for complex, multi-step financial instruments because the data is constantly being destroyed and scattered.
Just too fragmented.
Right. But this trade-off reveals the underlying philosophy of the network. Bitcoin's UTXO model is ruthlessly optimized to be exceptionally secure, verifiable, decentralized money. It intentionally sacrifices being a generalized world computer.
So it's not a flaw that it's hard to build flashy, decentralized apps on this base layer. It's a highly defensive design choice to protect its primary function as an incorruptible ledger.
Exactly.
That brings us to a really crucial question. If the network operates purely by destroying and creating these discrete chunks of coin, how do we actually instruct the network to move those chunks around?
The mechanics of it.
Yeah, like what does the anatomy of a transaction actually look like when you pull back the curtain?
At a mechanical level, a transaction is simply a structured list of inputs and a list of outputs, wrapped up with some metadata like a version number and a time lock.
Okay, inputs and outputs.
The inputs are simply cryptographic pointers. They tell the network, I want to destroy these specific existing UTXOs from previous transactions.
Right.
The outputs are the instructions for the brand new UTXOs you want to mint into existence. They specify two things: how much value the new chunk should hold, and what cryptographic locks should be placed on it to determine who can spend it next.
Okay, that seems straightforward.
And there is one golden, unbreakable rule governing this entire process. The total sum of the input values must be greater than or equal to the total sum of the output values. You cannot create money out of thin air.
I want to pause right there. Greater than or equal to. That phrasing implies there might be a difference between what goes in and what comes out.
Yes, there often is.
And diving into the material, this uncovers a mechanism that honestly sounds terrifying for a newcomer trying to build a transaction manually. The hidden fee equation.
Oh, yes, the fee trap.
I'm looking at the structure of a raw transaction, and there's no field anywhere that explicitly says, I'm paying a $5 network fee.
That is correct, and it is a detail that has burned many early developers. The network fee is entirely implicit.
Implicit, so it just figures it out.
It is simply whatever value is left over after all of the outputs are accounted for. The mathematical equation processed by the nodes is brutally simple. Total inputs minus total outputs equals the miner fee.
So let me make sure I am understanding the gravity of this mechanic.
Sure.
Let's say I am writing my own wallet software. I have a single UTXO sitting there worth 0.5 Bitcoin. I want to send my friend 0.3 Bitcoin.
Okay.
I construct the transaction. I list my 0.5 Bitcoin UPXO as the input. I list my friend's public address and 0.3 Bitcoin as the output. And then I just broadcast it to the network.
Without a change output.
Right. I forget to write the code that creates a change output to send the rest back to myself. Am I telling the entire network that the remaining 0.2 Bitcoin is just a generous tip for whatever miner processes my transaction?
Yes, you have just accidentally tipped the miner 0.2 Bitcoin.
But wait, 0.2 Bitcoin, depending on the market price. That could be tens of thousands of dollars.
Yeah.
Just instantly gone because of one missing output line. Is there a customer support line? Can I cancel it?
It is instantly, permanently, and irreversibly gone.
Wow.
The protocol has no concept of your intentions. It has no customer support. It simply executes the math it was given. If 0.5 goes in and 0.3 goes out, the remaining 0.2 is mathematically categorized as the fee.
That is brutal.
Whoever successfully mines the block containing that transaction will happily collect your massive donation.
So it's basically a very expensive typo.
Exactly. Now, practically speaking, everyday users don't construct raw transactions by hand in a command line interface. Modern wallet software handles this complex logic for you.
Oh, thank God.
Yeah. Behind the scenes, when you hit send, the wallet constructs the flow correctly. It takes the 0.5 Bitcoin input. It creates the 0.3 Bitcoin output to your friend. It calculates the precise required network fee based on current congestion. Let's say 0.0001 Bitcoin.
Right.
And then it automatically creates a crucial change output of 0.199 Bitcoin locked securely back to an address that you control.
Phew. Okay, thank goodness the software handles the heavy lifting. But it really highlights how unforgiving the base layer protocol is.
It really is.
And speaking of the wallet doing the heavy lifting, our documents spend a lot of time on a fascinating algorithmic challenge called coin selection.
Ah, yes, coin selection.
Because if I've been receiving weekly payments for years, I don't just have one big UTXO. I might have hundreds or even thousands of tiny little UTXOs scattered across my addresses.
And that presents a significant engineering hurdle. When you go to make a purchase, your wallet is essentially facing a complex optimization puzzle known in computer science as the knapsack problem.
The knapsack problem, like packing a bag.
Exactly. It has to look at your entire collection of unspent chunks and decide which specific combination of UTXOs to group together to cover the payment amount. Do you consolidate 50 tiny UTXOs into one transaction? The problem there is that every input you add requires a digital signature. Signatures take up betabytes. If you have 50 inputs, your transaction's data footprint becomes massive, which means you have to pay a much higher fee to the network just to get it processed.
So using a bunch of tiny coins is expensive.
Yeah.
But what's the alternative?
The alternative is using one massive UTXO to pay for a very small item. If you buy a coffee with a 10 Bitcoin UTXO, you generate a massive 9.999 Bitcoin change output.
What's wrong with that?
From a privacy perspective, an outside observer analyzing the blockchain can clearly see that a massive amount of wealth just moved, and they can likely deduce which output was the payment and which was the change, leaking information about your total net worth.
Oh, wow. I didn't even think of that.
Wallet developers spend years refining complex heuristics to balance the cost of fees, the creation of messy change, and the privacy of the user during coin selection.
It's like standing at the cash register with a massive jar of pennies and a $100 bill, trying to figure out the exact optimal combination to hand the cashier so you don't get too much heavy change back, but doing it mathematically in milliseconds.
That's a great way to think about it.
And while we are talking about these tiny amounts, the penny equivalents, there's another technical detail here that I find absolutely fascinating. The protocol, at its deepest level, never actually uses decimals.
Never. The concept of zero point 0.5 Bitcoin is entirely a user interface convenience created for humans to read on screens.
Really, no decimals at all.
At the core protocol layer, floating point mathematics, which is the standard way computers handle fractions and decimals, is strictly forbidden.
I can guess why. Anyone who has ever tried to add 0.1 and 0.2 in a programming language like JavaScript knows exactly what happens. You don't get 0.3, you get 0.3, 0.0000000000004. Because computers process information in binary ones and zeros, they cannot perfectly represent certain base 10 fractions. They have to approximate them, which leads to floating point rounding errors.
And in a global, mathematically enforced financial ledger, an approximation is unacceptable. A rounding error of a fraction of a cent, compounded across hundreds of millions of transactions over a decade, would destroy the integrity of the total money supply.
It would just drift out of balance.
Absolute integer-level precision is required. Therefore, everything in the system is measured in whole numbers. The base, indivisible unit of the network is the Satoshi, named after the pseudonymous creator.
The Satoshi.
Right. One Bitcoin is simply defined as 100 million Satoshis. So when you tell your wallet app to send 0.0001 Bitcoin, the protocol doesn't see a decimal. It simply sees the integer 10,000.
That is so elegant.
The entire global network is just adding and subtracting very large whole numbers.
That is such a clean solution to a notoriously messy computer science problem. Okay, so we've got inputs pointing to previous transactions, destroying them. We have outputs creating new integer amounts of Satoshis, and we have pointers connecting them all via transaction IDs or TXIDs.
Right.
But here is the critical security piece. How does the network know you are actually authorized to destroy that specific input? It can't just be about an address matching your name, because addresses are public.
Right. Anyone can look up an address.
Anyone can see them on a block explorer. So it has to be about solving a cryptographic puzzle.
This brings us to the locking mechanism, which is arguably the heart of the network's security. An output isn't just passively sitting at a public address waiting to be claimed. It is actively guarded by a tiny programmable piece of code.
Like a lock.
Exactly. We call this the locking script. When you want to spend that output later, your new transaction must provide an unlocking script. Every node on the network takes your unlocking script, concatenates it with the locking script, and executes the combined program. If the final mathematical result of that execution is true, the coins are authorized to move.
If it's false.
If the result is false, or if the program crashes, the transaction is immediately rejected by the network.
The documentation provides a great visual for this. A locking script is like a heavy combination padlock, but instead of just a standard number dial, it is a complex riddle written right on the side of it.
I like that.
The unlocking script is your specific answer to that riddle. You hand the padlock your answer, the network turns the gears of the program, and if the answer successfully solves the riddle, the padlock pops open and the money flows.
It is a highly accurate visualization, and the most common riddle on the network, the one securing hundreds of billions of dollars of value, is conceptually simple.
What is it?
It's essentially prove that you own the private cryptographic key that mathematically corresponds to this specific public key by providing a valid digital signature for this transaction.
I want to dig into that concept of public and private keys, because we throw the term elliptic curve cryptography around, but what does that actually mean for the security of this lock?
Elliptic curve cryptography, or ECC, is the mathematical bedrock here. Imagine a specific mathematically defined curve plotted on a graph. To generate a key pair, the system picks a random point on that curve. That massive random number is your private key.
Okay, random point is the private key.
Then it performs a mathematical operation. It draws a line tangent to that point, finds where it intersects the curve again, and reflects it across the axis. It repeats this process thousands of times. The final destination point is your public key.
It's a very specific path.
Yes. The beauty of this math is that it is a trapdoor function. It is incredibly easy for a computer to start at the private key and calculate the public key. But it is practically impossible, even if you had all the supercomputers on Earth running for 1 billion years, to start at the public key and reverse engineer the math to find the private key.
So the network uses that trapdoor. You show them the public key, you use your private key to generate a signature, and the network can verify the math without ever seeing your private secret.
Exactly.
But the language used to write these riddles, this combination of locking and unlocking scripts, it's called Bitcoin script. And reading through the technical stacks, it's fascinatingly restrictive.
Highly restrictive.
It's a stack-based language. It uses primitive opcodes like OPDUP, which duplicates the top item of data, or OP checks SIG, which validates those elliptic Kerr signatures.
Yeah.
But crucially, the language is entirely non-Turing complete.
Right, non-Turing complete.
It has absolutely no loops. You cannot write a while loop or a for loop. Why would software engineers intentionally design a programming language to be less powerful?
It comes down to a fundamental prioritization of security and predictability over flexibility. This is a brilliant defensive engineering choice.
Defensive how?
Well, if a programming language is Turing complete, like Ethereum's Solidity language, it can theoretically compute any program you can imagine. But it is also susceptible to a foundational computer science dilemma known as the halting problem, first identified by Alan Turing.
A halting problem.
Yes. You cannot mathematically know in advance if a complex program will eventually finish running, or if it will get stuck in an infinite loop forever.
Let me guess. If you allow infinite loops on a decentralized network where thousands of nodes have to execute every line of code,
An attacker would immediately exploit it. They could broadcast a transaction with a tiny, deceptively simple script that simply loops infinitely.
oh wow.
Every single node on the network would receive that transaction, attempt to validate it, enter the infinite loop, and freeze. The entire global network would grind to a halt. It would be a catastrophic, zero-cost denial-of-service attack.
So by removing loops, they fix that.
By removing the ability to loop entirely, Bitcoin script guarantees that every single program will terminate and will do so in a fraction of a millisecond. It makes validating transactions incredibly cheap, fast, and entirely predictable.
They viewed this not as a general-purpose computer, but as secure money plumbing.
That's a perfect way to put it, money plumbing.
It's not trying to run video games. It's just trying to move value securely.
Yeah.
Let's look at how this plumbing has evolved, because if you look at the raw data of addresses over the years, the formats change.
Yes, they do.
The classic one, the original from the Genesis era, is called P2PKH pay to public key hash. These are the addresses that start with the number 1.
Yes. The locking script for P2PKH is the classic riddle we just discussed. It demands a public key and a valid digital signature. But there is a subtle, brilliant privacy feature built into it.
What's up?
The address you give to your friend isn't actually your full public key. It is a cryptographic hash, a scrambled, shortened version of your public key. What's fascinating here is that your actual full public key is not revealed to the public blockchain until the very moment you attempt to spend those coins.
Wait, really? So while the money is just sitting there, nobody knows the actual geometry of your public key?
Correct. It is hidden behind the hash. This provides an incredible layer of forward-looking security.
How so?
Let's imagine that 20 years from now, quantum computers become powerful enough to crack elliptic curve cryptography and reverse engineer private keys from public keys.
The nightmare scenario.
Right. Even if that happens, the attacker wouldn't be able to steal funds sitting in unspent P2PKH addresses, because the public key isn't on the blockchain yet to be attacked. They only have the hash, and quantum computers are not particularly good at breaking hashes.
That is incredible foresight from the developers.
Yeah.
Then moving forward in time around 2012, we see the introduction of addresses starting with the number 3, P2SH, or pay-to-script hash.
P2SH was a major evolution in how we use that plumbing. It allowed users to lock coins not just to a single public key, but to an arbitrarily complex script.
Okay, give me an example.
The most common use case is a multi-sig contract requiring, say, 2 out of 3 business partners to sign a transaction before the corporate funds can move. But putting a massive, complex locking script on the blockchain takes up expensive block space.
Because data is money.
Exactly. P2SH solved this by allowing the sender to lock the coins merely to the hash of that complex script.
So the sender doesn't even need to know the complex rules. They just send it to a short hash. And the recipient only reveals the complex, heavy script when they go to unlock it and spend the money.
Precisely. It shifted the burden of data storage and complexity away from the sender and placed it squarely on the receiver, vastly improving the efficiency of the network.
And then we move into the modern era with SegWit and Taproot. addresses starting with BC1Q and BC1P. We are going to dive incredibly deep into those when we talk about network upgrades, because they fundamentally rewrite how the data is structured to achieve massive scaling.
Right.
But right now, I want to pivot our focus. We know how secure these cryptographic locks are. We know exactly how the UTXOs are destroyed as inputs and created as outputs. But a massive glaring question remains.
Where does it all come from?
Yes. If every transaction requires existing UTXOs as inputs, where do the very first UTXOs come from? How was a Bitcoin actually born?
That is the fundamental question of issuance and monetary policy. In a traditional fiat system, issuance is subjective. A central bank or a government committee convenes, analyzes the economy, and decrees that new money must be created, usually by issuing debt or digitally crediting a ledger.
They just type it into existence.
Right. In this decentralized system, there is no committee. There is only one authorized, mathematically strictly enforced mechanism for new money to enter circulation, and it happens through something called the Coinbase transaction.
Just to clarify immediately for anyone listening, we are talking about the technical term Coinbase transaction.
Right.
We are absolutely not talking about the publicly traded cryptocurrency exchange named Coinbase, correct?
Correct. There is no relation. The exchange named itself after the technical term. The Coinbase transaction is simply the very first transaction included in every newly mined block.
Okay.
And it is structurally unique compared to everything we've discussed so far. A Coinbase transaction has no normal inputs. It does not point to any previous transaction. It does not destroy any existing UTXOs.
Because there's nothing to destroy.
Exactly. Instead, it is authorized by the protocol rules to create brand new coins out of thin air, and it assigns those newly minted coins as an output to the miner who successfully expended the energy to find that block. This newly minted amount is referred to as the block subsidy.
And this subsidy is the absolute heart of Bitcoin's economic policy. Because the developers didn't just pick a flat rate and leave it running forever. Let's break down the timeline of this issuance because it is dramatic.
Very dramatic.
When the network launched in January 2009, that very first block, the Genesis block, rewarded the miner with 50 Bitcoin. 50. And that happened every 10 minutes. But the protocol dictates that this block subsidy gets cut exactly in half every 210,000 blocks.
Which works out to roughly every 4 years.
Right. That cyclical event is what the community and the market refer to as the halving.
The halving, yes.
So we go from 50 coins every 10 minutes in 2009. 4 years later in 2012, it has to 25. In 2016, it has to 12.5, down to 6.25 in 2020. And as of the most recent halving in April 2024, the block subsidy dropped to just 3.125 Bitcoin per block. And here's where it gets really interesting. We always hear the phrase, the 21 million coin cap, the promise that there will never, ever be more than 21 million Bitcoin in existence. But reading the code, there isn't a single line of code that says, stop at 21 million. It's just the emergent result of math, isn't it?
It is pure, inescapable mathematics. The 21 million cap is the result of a geometric series.
A geometric series.
You take that starting reward of 50, and you add the next epoch of 25, and you add 12.5, and you carry that fractional series out infinitely, multiplying each term by the 210,000 blocks per epoch. The sum of that series converges. It asymptotically approaches 21 million.
It just naturally hits that ceiling.
In fact, because the protocol eventually runs out of decimal places and rounds down to the nearest whole integer Satoshi, the true final supply will actually be slightly under 21 million. It mathematically stops at exactly 20,999,999.97.
And looking at the network data today, we are already incredibly close to that limit. As of early 2026, roughly 19.95 million Bitcoin have already been mined and issued into circulation. That is 95% of the total supply that will ever exist already out in the world.
It's wild to think about.
It really is. The remaining 5% will slowly, agonizingly trickle out over the next century until the final fraction of a Satoshi is mined around the year 2140. But I want to push back on the security of this cap.
Sure.
If the miners are the ones securing the network and they're the ones building the blocks, why couldn't a cartel of massive mining companies just collude, rewrite the open source software to ignore the halving, and start minting 50 Bitcoin per block again to enrich themselves?
It is a logical question, and it speaks to the genius of the network's incentive structure. The miners propose blocks, yes, but they do not dictate the rules.
Who does?
The rules are enforced by the tens of thousands of independent nodes running worldwide, the users, the exchanges, the wallet providers. If a cartel of miners modified their software to mint 50 Bitcoin today, they would successfully create a block. But the moment they broadcast that block to the rest of the network, every single independent node would check the math, see the invalid subsidy amount, and instantaneously reject the block.
The miners would just be burning millions of dollars of electricity to produce invalid blocks that the rest of the economy completely ignores.
Exactly. They would essentially fork themselves off the network into irrelevance. The 21 million cap isn't just a line of code. It is protected by the immutable laws of human incentive. The nodes, the people holding the currency, will never voluntarily download a software update that dilutes their own wealth.
That makes a lot of sense.
This mathematical certainty is why economists and advocates refer to Bitcoin as the hardest money ever created. Think about traditional fiat currencies. When a government faces a crisis, a war, or a pandemic, the central bank can, and historically always does, expand the money supply. This dilutes the purchasing power of every existing dollar or euro.
And even physical gold has inflation.
Yes. Even physical gold has a fluctuating inflation rate. If the market price of gold spikes, mining companies immediately invest in better excavation equipment, they open new mines, and the physical supply of gold entering the market increases, which eventually suppresses the price.
But this system is completely immune to that supply response. If the price goes to $1 million a coin tomorrow, and every single computer and power plant on Earth turns on to mine it, the network will not produce one single extra fraction of a coin beyond the scheduled 3.125 per block.
Exactly.
It is absolutely mathematically inelastic.
Which is a profound paradigm shift in monetary economics. But, as you astutely noted, all of this, the halving schedule, the geometric series, the entire issuance model, relies on one crucial underlying variable.
The 10-minute block.
Right. It relies on a new block being discovered roughly every 10 minutes. If blocks are found faster, the supply schedule accelerates. If slower, it decelerates. But we just talked about how anyone in the world can turn a mining rig on or off at any time. The global computing power, the hash rate, is wildly unpredictable.
So how does a decentralized network, with no central server coordinating things and no master clock, manage to keep perfect time against a chaotic global environment?
This is where we look at the difficulty adjustment algorithm, which the documentation essentially describes as the metronome of the network.
The metronome.
The protocol has a hard-coded target, one block every 10 minutes. But if the price surges and 1 million new mining machines come online, suddenly the global hash rate doubles. If the cryptographic puzzle they are trying to solve stayed at the exact same difficulty, they would start finding blocks every 5 minutes. The 4-year halving cycle would suddenly become a 2-year cycle.
So the network has to have a way to fight back against the miners.
It does, by continuously observing its own performance. The network waits for an epoch of exactly 2,016 blocks to pass. At the target rate of exactly 10 minutes a block, 2,016 blocks should take precisely 2 weeks of wall clock time to mine.
Okay, 2 weeks.
When that 2016th block is finally found, every single node on the network independently looks back at the timestamps and measures the actual time it took to complete that epoch.
I think of it like a smart treadmill that is automatically tracking a runner's heart rate.
Oh, I like that.
Yeah, the machine's target is to keep your heart rate at exactly 150 beats per minute. If you start running too fast and your heart rate drops because you are getting fitter, the treadmill senses the discrepancy and automatically increases the incline. It forces you to work harder, slowing your pace back down to the target rate.
That is an excellent analogy. In engineering terms, it is a closed negative feedback control loop. If the network discovers those 2,016 blocks in only 10 days instead of 14, it means the global mining power was too high. The network automatically, mathematically, increases the difficulty of the cryptographic puzzle, making it significantly harder to find the next block.
And if the opposite happens?
If, conversely, a massive regulatory crackdown or a regional blackout takes half the miners offline, and those blocks take 3 weeks to find, the network automatically decreases the difficulty, making the puzzle easier. The adjustment is strictly proportional, steering the average block discovery time back to exactly 10 minutes, regardless of whether 1,000 laptops or 1 million industrial supercomputers are mining.
But diving into the statistical data highlights a really crucial gotcha here. We keep saying 10 minutes. But that is strictly a statistical average over long periods. It's not a dependable train schedule. If I am waiting for my transaction to clear, I can't just set a timer for 10 minutes.
No, you cannot. And this is a fundamental reality of proof of work. Block discovery is a stochastic process. It follows a Poisson distribution, specifically an exponential memoryless distribution. Every single hash a miner computes is like rolling a multi-billion-sided die.
Right.
The fact that the entire global network has been rolling the die furiously for 9 minutes without a success does not mean a success is due in the next minute.
The dice have no memory.
Yeah.
The probability of finding a block right now is exactly the same as it was 10 minutes ago.
Precisely. So in reality, the spacing between blocks is wildly erratic. You might see 2 blocks discovered just seconds apart, and then you might see a terrifying drought where the network goes 50, 60, even 80 minutes without a single block being found anywhere on Earth.
Wow, 80 minutes.
Yeah, the variance is wild, even if the long-term 2-week average perfectly tracks to 10 minutes.
And this statistical reality is exactly why exchanges and merchants require what are called confirmations. If I'm buying a house or a car with Bitcoin, the seller isn't going to hand me the absolute second my transaction appears in a block, right? Because of that variance, things can get messy at the tip of the blockchain.
They absolutely shouldn't hand over the keys immediately. Because of the stochastic nature of mining, 2 different miners on opposite sides of the planet might find a valid block at nearly the exact same time. This creates a temporary, localized fork in the chain.
Like a split road.
Right. Some nodes see block A first, some see block B first. The network resolves this by simply waiting for the next block. Whichever chain grows longer first becomes the canonical truth, and the other block is orphaned and discarded by the network.
And what happens to the transactions in the orphan block?
If your transaction was in the discarded block, it goes all the way back to the waiting room. A confirmation is simply a new block being cryptographically stacked on top of the block that contains your transaction.
So every new block buries your transaction deeper in the ledger.
Yes. The industry standard is to wait for 1 confirmation for small purchases like a coffee, maybe 3 confirmations for a car, and 6 confirmations, which takes about an hour on average for moving millions of dollars. With every block buried beneath another, the amount of computational energy required for an attacker to rewrite the chain and reverse that transaction becomes exponentially more mathematically impossible.
Okay, so blocks arrive roughly every 10 minutes on average, but with high variance. And as we learned earlier, each block has a heavily restricted data capacity. It's capped at what the protocol technically calls 4 million weight units.
Right, which translates to roughly a few megabytes of data depending on the transaction types.
So block space is a highly artificially scarce resource. What happens when the whole world tries to rush through a door that only opens every 10 minutes and only fits a few thousand people?
You get a fiercely competitive global bidding war. Because the space inside the next block is strictly limited, users must financially bid against each other to convince a profit-seeking miner to include their specific transaction. This dynamic creates the fee market.
And this is where another mind-bending fact for traditional finance folks comes in. In the legacy banking world, fees are almost always calculated as a percentage of the value being moved. If you wire $1 million internationally, the bank takes a much bigger cut than if you wire $100.
Always.
But in this protocol, sending 0.001 Bitcoin and sending $1 billion costs the exact same fee, provided their data footprint is identical.
That is a critical conceptual distinction. On this network, you are not paying for the transfer of monetary value. You are paying for the consumption of digital real estate. You are buying block space.
Block space, okay.
Therefore, fees are priced solely by the byte size of your transaction, expressed as satoshis per virtual byte, or SAT per VB. A simple transaction with 1 input and 2 outputs might be around 140 virtual bytes. It doesn't matter if that input is worth $5 or $500 million. The data weight is the same, so the fee to the miner is the same.
So how does this bidding war actually play out in real time? If I initiate a transaction on my phone, where does it go before it gets cemented into a block? It doesn't just float in the ether.
It goes into the mempool. The mempool, short for memory pool, is essentially a chaotic, decentralized, network-wide waiting room of unconfirmed transactions. Every single node keeps its own mempool in its local RAM.
Like a holding pen.
Yes. When you broadcast your transaction, it propagates across the globe and sits in these waiting rooms. Now, miners are economically rational actors. They have incredibly high electricity bills to pay. They want to maximize their profit for every block they mine. So when they are assembling the puzzle for the next block, they look at their local mempool, they sort all the waiting transactions by their fee rate, the highest Satoshis per virtual byte, and they greedily pack their blocks starting from the highest bidders down until the block hits the data cap.
I want to walk through a worst-case scenario here. Let's say I initiate a transfer. The network is normally quiet, so my wallet suggests a lowball fee of 2 Satoshis per virtual byte. I get sent.
Okay.
But suddenly, a massive speculative mania hits. Like that massive surge we saw in 2023 with the ordinals and inscriptions, where people were suddenly bidding huge amounts of money to permanently etch images and data onto the blockchain. Suddenly, everyone globally is bidding 100 Satoshis per virtual byte. Is my transaction just stuck in that waiting room forever? Am I completely paralyzed?
If the congestion doesn't clear, yes, your transaction could sit in the mempool in a state of limbo for days or even weeks. And if the mempool gets too full, individual nodes might just drop your low-fee transaction from their memory entirely to save RAM, at which point it's as if you never sent it. The funds just reappear as spendable in your wallet. But the protocol provides incredibly clever emergency levers for exactly this scenario. You are not helpless.
Let's pull those levers. How do I rescue my stuck transaction?
The first and most common tool is called RBF, or Replace by Fee. If your wallet software supports this and you flag the initial transaction correctly, you can essentially rebroadcast the exact same transaction, spending the exact same UTXOs, but you attach a significantly higher fee.
Oh, nice.
It's akin to walking up to the bouncer at a crowded exclusive club, realizing your $20 tip didn't get his attention, and handing him a $50 bill instead. The network sees the new transaction, recognizes it mathematically conflicts with the old one by spending the same inputs, but sees the higher fee and replaces the old, stuck one in the mempool with the new lucrative one.
That's convenient if I am the sender. But what if I'm the recipient? What if a client owes me money, they send it, but they lowball the fee, and I'm desperately waiting for those funds to clear so I can pay my rent? I can't use Replace by Fee because I don't control their private keys to re-sign the transaction. Am I just at the mercy of the network?
In that specific case, you can utilize a brilliant mechanic called CPFP, which stands for Child Pays for Parent.
Child pays for parent.
Yes. Remember, your wallet software can see that unconfirmed transaction sitting in the mempool. It knows mathematically that those funds are destined for your address. So you create a brand new transaction, the child, that attempts to spend the output of that stuck, unconfirmed transaction, the parent.
Right.
But on this new child transaction, you attach an astronomically high fee, a fee so exceptionally large that it economically covers the cost of both the child and the parent transactions combined.
Oh, I see where this is going.
Yeah.
You are basically dangling a massive carrot in front of the miner.
You are forcing the miner's hand through sheer economic incentive. The miner looks at the mempool and desperately wants to claim the massive fee from your child transaction.
But they can't process the child without the parent.
Exactly. The strict rules of the blockchain dictate that a child transaction is completely invalid and cannot be included in a block unless its parent transaction is also included first. So, to get the juicy fee they want, the miner's software uses package relay logic. It mathematically groups them together, scoops up the stuck parent transaction, and processes them both simultaneously in the very next block.
That is a brilliant piece of decentralized incentive engineering. But stepping back, it also highlights a glaring practical reality. Navigating intense fee markets, tracking Satoshis per virtual byte, waiting for stochastic 10-minute block averages, dealing with sudden mempool congestion. This is all perfectly acceptable if you are moving a corporate treasury or settling $1 billion international bank transfer.
It's fantastic for that.
It operates flawlessly as a global settlement layer, but it is absolutely terrible for buying a cup of coffee.
Yeah.
The base layer mathematically maxes out at roughly 7 transactions per second globally. Visa routinely handles tens of thousands. How does a protocol like this scale to handle the real world without compromising that pristine, secure base layer we just spent an hour dissecting?
The answer is that it scales in layers. The developer community surrounding this protocol has a very strict, almost religious philosophy. You do not alter the base layer to accommodate speed or throughput if it even slightly sacrifices decentralization or security.
So no compromising the base.
Never. Major protocol upgrades are incredibly conservative, heavily debated for years, and they're almost always executed as soft forks.
Explain the difference between a hard fork and a soft fork for us.
A hard fork is a permanent divergence in the rules where the new version is incompatible with the old version. If you don't upgrade your node software, you get kicked off the network. It splits the community.
Right, like a messy divorce.
A soft fork, however, is a backward compatible rule change. It typically tightens the rules rather than expanding them. The beauty of a soft fork is that if you are a user running an old node in your basement and you decide you don't want to upgrade, you don't have to. Your node will still accept the new blocks, the network remains unified, and you can opt in to the new features whenever you are ready.
And looking at the history, two massive soft forks paved the way for scaling and efficiency. The first major battleground was SegWit in 2017, which stands for Segregated Witness.
Yes. SegWit was born out of a very contentious, multi-year period in the community known as the block size wars. One faction wanted to simply hard fork the network and make the blocks larger, from 1 megabyte to 8 or even 32 megabytes to fit more transactions.
To make the door wider.
Right. But the SegWit faction argued that bigger blocks would make running a node too expensive for average people, centralizing the network. They argued for optimizing the space we already had. SegWit did several clever things, but its most critical foundational fix was ending a bug known as transaction malleability.
I want to dig into malleability because it sounds like a massive security flaw. What does it mean to malleate a transaction?
It relies on a mathematical quirk in the ECDSA digital signatures used at the time. When you sign a transaction, you generate a cryptographic signature. But because of how the elliptic curve math works, a malicious third-party node sitting on the network could intercept your unconfirmed transaction in the mempool, take your signature, and mathematically invert a specific value inside it, the S value.
And that invalidates the signature.
That's the wild part. It doesn't invalidate the signature.
Wait, really?
The math still checks out, the lock still opens, and the coins still go to the exact right destination. No money is stolen. But because the literal bytes of data in the signature have been altered, when the network hashes the entire transaction to generate the transaction ID, the TXID, the hash comes out completely different.
So the transaction goes through, but the receipt number changes while it's in flight.
Yeah.
That sounds like a nightmare for anyone trying to systematically track a payment.
It was an absolute nightmare for software developers. If you built a secondary system or a layer 2 network that mathematically relied on pointing to an unconfirmed TXID as a foundation, and someone on the network malleated it and changed the TXID before it confirmed, your entire secondary system broke.
That's a huge problem.
SegWit brilliantly fixed this by segregating the witness. It took the signature data, the witness, and moved it completely out of the calculation of the TXID. It put the signatures in a separate data appendix. This made transaction IDs permanently cryptographically stable.
And as a massive bonus, because of how they structured that appendix data, SegWit introduced the concept of weight units that we mentioned earlier. It effectively gave a massive mathematical discount to signature data, organically increasing the functional capacity of a block from 1 megabyte up to nearly 4 megabytes without ever executing a hard fork.
It's an incredibly elegant compromise.
And fixing that malleability issue laid the concrete foundation for the next major upgrade, Taproot, in 2021.
Taproot is a masterclass in beautiful cryptography. The headline feature of Taproot was the introduction of Schnorr signatures, replacing the old ECDSA signatures for those who opted in.
Schnorr signatures?
Yes. Schnorr signatures are mathematically cleaner, they are slightly smaller in byte size, but their absolute superpower is that they are linear.
Linear meaning they can be added together like simple algebra.
Exactly. Linear signature aggregation. Let's revisit that complex smart contract scenario. Suppose a massive corporation has a multi-sig treasury address that requires signatures from 3 different executives' hardware wallets to unlock the funds.
Okay.
Before Taproot, all 3 of those massive individual signatures had to be published directly onto the public blockchain. This took up a huge amount of expensive block space, and more importantly, it publicly broadcast to the entire world, hey, this is a complex, multi-party, corporate account moving funds.
But with Schnorr signatures via Taproot.
With Schnorr, those 3 executives can communicate off-chain, mathematically add their 3 private signatures together, and generate one single aggregated signature. When they publish that to the blockchain, it is vastly smaller, saving them massive amounts in fees.
And the privacy.
Crucially, to anyone analyzing the blockchain, that aggregated multi-sig transaction looks absolutely cryptographically identical to a standard single-person payment.
So it vastly improves efficiency by reducing the data footprint. And it massively improves privacy because nobody, not chain analysis firms, not competitors, can tell the difference between my simple coffee purchase and a complex billion-dollar corporate multi-sig settlement.
It's remarkable.
But even with SegWit expanding the blocks and Taproot making transactions smaller and more private, Layer 1 is still fundamentally capped by the physics of the 10-minute block interval. To achieve true Visa-level global scaling, we have to take the traffic off-chain. And that brings us to the Lightning Network.
The Lightning Network is the premier Layer 2 scaling solution, and it is a completely different paradigm of transacting.
I want to use the bar tab analogy here, because when I was reading the Lightning documentation, this was the only way I could visualize the cryptography.
It's the best way to visualize it.
Imagine you walk into a crowded, incredibly busy bar on a Friday night. You want to buy a drink. You can swipe your credit card. But if you swipe your card for every single $5 beer all night long, the bartender hates you because it slows everything down.
Right.
The credit card company is charging a flat 3% settlement fee on every single tiny transaction, and the global network is getting clogged with microscopic data points.
It is the definition of inefficient microtransacting.
Right. So what do you do instead? You open a tab. You hand the bartender your card exactly once at the start of the night. You sit there for 3 hours. You order 5 drinks. You buy your friend around. You just keep verbally tallying it up on a piece of paper.
Okay, yeah.
This is all off-chain. It is instant. There is zero network fee. It's just you and the bartender locally agreeing on the new balance. And then at the very end of the night, you close the tab. The bartender runs your card exactly one time for the net total of $50. The bank, the underlying settlement layer, only ever sees one single efficient transaction.
That analogy perfectly captures the essence of a Lightning payment channel. When two parties, let's call them Alice and Bob, know they want to transact frequently, they don't use the base layer for every payment.
They open a tab.
Exactly. Instead, they create a single on-chain transaction. They lock up some Bitcoin together in a 2 of 2 multi-sig address. That single layer 1 transaction opens the channel. It is the equivalent of handing the bartender your card to open the tab.
So the money is locked on the main blockchain, but the channel is open. What happens next?
Now, Alice and Bob have a secure, direct, peer-to-peer internet connection. Alice can send Bob a fraction of a penny instantly, 1,000 times a second if she wants to. They do this not by broadcasting to the network, but by cryptographically signing updated balance sheets and passing them back and forth directly to each other over the internet.
So it never touches the main blockchain?
These intermediate updates never touch the blockchain. There is no 10-minute wait for a block. There is no miner fee. It is operating at the speed of light.
But I see a massive vulnerability here. What stops Alice from cheating? Let's say Alice funds the channel with 1 Bitcoin. She buys 0.5 Bitcoin worth of goods from Bob over a week. Her real balance is now 0.5.
Okay.
But she still has the very first signed balance sheet sitting on her hard drive, the one that says she owns the full 1 Bitcoin. What stops her from taking that old, stale balance sheet, publishing it to the Layer 1 blockchain, and stealing her money back?
That exact vulnerability is why Lightning took years to develop. The solution is the cryptographic penalty mechanism built into the protocol. Every single time Alice and Bob sign a new balance sheet, they simultaneously exchange cryptographic revocation keys. These keys actively invalidate the old balance sheet.
How does a revocation key work?
If Alice attempts to cheat, she broadcasts that old, stale state to the Layer 1 blockchain. But the blockchain gives Bob a time window, usually a few days, to contest it.
Oh, so Bob has time to catch her.
Right. Bob's node, which is monitoring the blockchain, immediately recognizes the old state. Bob can take the revocation key that Alice gave him previously, present it to the smart contract, and cryptographically prove to the base layer that Alice is lying.
And what's the penalty?
The penalty for lying is absolute. The smart contract allows Bob to sweep 100% of the funds in the channel. All of Alice's remaining money is confiscated and given to Bob. The mathematical punishment for cheating is so devastatingly complete that it keeps all rational actors perfectly honest.
Wow, okay. That secures a direct channel between two people. But I don't want to open a direct funded bar tab with every single merchant in the world. I don't want to lock up my capital in a channel with a coffee shop in Paris that I'm only going to visit one time in my life. The capital inefficiency would be absurd.
And you don't have to, because Lightning is a network of interconnected channels. If Alice has a well-funded open channel with her friend Carol, and Carol happens to have an open channel with Bob, the Parisian coffee shop owner, Alice doesn't need to connect to Bob directly.
She can route it.
Alice can route her payment to Bob through Carol.
But wait, if I am routing my money through Carol's computer, how do I know Carol won't just steal my money while it's passing through her node? We are back to needing trust.
We eliminate the need for trust through the use of HTLC's hashed time-locked contracts. This is where the restricted, predictable nature of Bitcoin script really shines.
Okay, how does an HTLC work?
An HTLC is a cryptographic smart contract that wraps the payment. It essentially says to the intermediary, Carol, I will route this money to you, but it is cryptographically locked. You can only claim this money if you can mathematically prove that you already forwarded the equivalent amount to Bob within the next few hours.
And if she doesn't?
If you cannot provide the cryptographic proof from Bob, the contract automatically dissolves and the money safely refunds back to Alice. The money is mathematically locked in transit. No intermediary can steal it. It either securely reaches the final destination or it fails safely and bounces back to the sender.
It is breathtaking engineering. It solves the speed and cost issues elegantly. But in the spirit of intellectual honesty, our documentation points out the significant trade-offs here. Lightning is not a magic wand that solves everything without friction.
Definitely not.
It requires inbound and outbound liquidity. You can only send as much money as is funded in your side of the channel. Furthermore, it requires your node to be online continuously to watch for those cheating attempts we talked about.
Sure.
It is a massive increase in operational and technical complexity. You are trading the dead simple passive security of the base layer for speed and low cost.
It is a profound trade-off, and it is entirely intentional. Running a well-connected Lightning routing node for a business is a serious, full-time engineering undertaking. It requires capital management and server maintenance.
Right.
But the developers accepted that burden at Layer 2 precisely because it allows the Layer 1 base layer to remain completely uncompromised, decentralized, and mathematically secure for everyone.
Which brings us to the grand synthesis of everything we've covered today. We have spent the last hour dissecting all of these technical realities, the deeply counterintuitive UTXO model, the deliberately handicapped, loop-free script language.
The unforgiving 10-minute blocks.
Right. And the absolute, mathematically enforced 21 million cap. The complex, highly technical Layer 2 scaling with HTLCs. All of these deliberate, sometimes frustrating engineering choices culminate in Bitcoin's ultimate identity in the wider financial world. Why is this specific network, despite being technically slower and structurally simpler than 100 newer, flashier blockchains, worth roughly half the value of the entire global crypto market?
If we connect all of these mechanical choices to the bigger picture, it fundamentally comes down to trust, immutability, and time. In technology and economics, there is a powerful concept known as the Lindy effect.
The Lindy effect.
The Lindy effect states that the future life expectancy of a non-perishable thing, like a technology, a protocol, or an idea, is directly proportional to its current age. The longer something survives under pressure, the more likely it is to continue surviving into the future.
That makes sense.
Bitcoin launched in January 2009. It ran for years in complete obscurity, maintained by volunteers. It has been under constant, relentless attack from hackers testing its cryptography. It was mocked by traditional finance for a decade. It dealt with massive internal civil wars over block sizes and protocol direction. And through it all, it never broke.
It never broke.
For a global system designed from the ground up to be a sovereign store of value, the sheer act of not breaking for over a decade and a half is, in itself, the ultimate killer feature.
It survived the crucible.
Oh.
And because it survived, the global narrative shifted dramatically. It stopped being viewed merely as digital cash for buying coffee, and it transformed into the digital gold thesis.
Right, digital gold.
It has all the monetary properties that historically made physical gold valuable. It is fundamentally scarce, it requires real-world energy to produce, and it exists outside the direct control of any single government or central bank. But it improves on physical gold immensely.
Oh, massively.
You can divide it into 100 million microscopic pieces with perfect precision. You can cryptographically verify its complete authenticity in milliseconds without needing to hire a metallurgist to do a chemical assay. And most importantly, you can teleport $1 billion of it across the planet in 10 minutes just by sending a secure digital message over the internet.
And its security moat is entirely unmatched in the digital realm. To execute a 51% attack, to try and rewrite the recent history of the blockchain to reverse a transaction, an adversary would need to physically acquire and power enough specialized, custom-built ASIC computing hardware to outcompute the entire honest network combined.
Which is practically impossible at this point.
We are talking about tens of billions of dollars in highly specialized hardware, and securing the energy output equivalent to a small nation just to attempt to double spend a few recent transactions. And even if they achieved that impossible feat, they still couldn't steal anyone else's private keys, and they could never print money past the mathematically enforced 21 million cap. The proof of work moat is virtually impenetrable.
And we should note, purely as a factual trade-off explicitly outlined in our sources, that the massive energy consumption required to secure that proof-of-work mode is the center of a very real ongoing debate regarding electricity use and ESG concerns. It takes immense real-world energy to maintain that impenetrable wall of cryptographic security.
It does. It is the explicit cost of achieving absolute decentralized security without relying on a central authority. There is no CEO to subpoena or pressure. There is no foundation or board of directors that controls the protocol.
Just code.
The network is maintained by tens of thousands of independent nodes running in basements, offices, and data centers worldwide, all voluntarily running code that enforces the exact same mathematical rules.
And that uncompromising resilience is what finally broke the dam of traditional finance. The network effect became too massive, too undeniable to ignore. The liquidity attracted more liquidity. And this culminated in a historic moment in January 2024 with the approval of spot Bitcoin ETFs by regulators in the United States.
That was the turning point.
That was the bridge. Suddenly, the hardest money ever created, secured by this anarchic, decentralized network of cryptography, hashing power, and game theory, was available to be purchased in the boring, traditional brokerage accounts of massive pension funds and everyday retail investors worldwide.
It is the ultimate realization of its initial design architecture. The developers deliberately, stubbornly chose to prioritize sound money, absolute scarcity, and uncompromising security over high throughput and complex programmability.
It didn't budge.
They pushed the speed to layer 2 with Lightning, they left the complex smart contracts to alternative networks, and they protected the base layer at all costs. And the global market has overwhelmingly validated that decision. The limitations of the protocol are not flaws, they are the structural, load-bearing pillars of the entire system.
Okay, we've covered a truly massive amount of ground today. We started by shattering the illusion of accounts, learning how UTXOs are destroyed and created like physical cash. We deciphered the hidden fee traps in raw transactions and unlocked the padlock riddles of Bitcoin script.
We really went deep.
We did. We traced the mathematical certainty of the 21 million cap, guided by the relentless metronome of the difficulty adjustment algorithm. We navigated the chaotic mempool bidding war, and we explored exactly how SegWit, Taproot, and the Lightning Network evolved the protocol without breaking its foundations. All of it proving that Bitcoin's perceived limitations are exactly what makes it unbreakable. So, what does this all mean for you?
I want to leave you with a thought that builds on everything we've discussed today, highlighting a genuinely open, unresolved debate in the architecture of the system.
Let's hear it.
We know the 21 million cap is absolute. We know the block subsidy halves every 4 years. That guarantees scarcity, but it also mathematically guarantees that the block subsidy, the newly minted coins that currently pay the miners to secure the network, will eventually drop to absolute zero.
To zero.
A century from now, around the year 2140, there will be no block reward. The trillion-dollar security of the entire global network will rely entirely on the transaction fee market we explored today. The miners will only be paid by the small fees users attach to their transactions for block space.
So what's the question?
The provocative question is this. In a future world where Layer 2 networks like Lightning are perfectly optimizing and minimizing on-chain transactions to save money, will there be enough organic fee revenue generated every 10 minutes to incentivize miners to keep their massive facilities running? Are future generations willing to pay enough in block space rent to secure the hardest money ever created?
Wow. I want you to let that sink in. The mechanical engine we looked under the hood of today is beautiful, it is robust, but its final, ultimate equilibrium is a test of human economics that won't fully resolve for another 100 years. Thank you for joining us as we put on the overalls and explored the incredible machinery of digital gold. We'll see you on the next Deep Dive.